All right. What we have here is we know in this case the true probability of a student saying that they want coffee more, right? So the true probability is 65, but we selected 100 students and we asked them which they prefer. So we want the probability that 78 or more would say coffee, even though kind of the true probability is 65%, right? So here we're saying more than 78 students. So what we want is we want the probability of more than 78. So the probability of more than 78 is the same as the probability of, so 1 minus the probability of 78 or less, right? Because we want strictly more than 78, not 78 or more.
Right.
So that would be 1 minus p binom. So q is equal to 78. So and then size is equal to 100 and prob is equal to 0.65. So that's the true probability. So this is like the probability of 78 or fewer. 1 minus that would be more than 70, right? So you can look at this probability. So that's what you get. So now what we want is we want the same thing but with a normal approximation, right? So the normal approximation to the binomial is the mean is n times p, and the standard deviation is square root of p times 1 minus p times n, right? So the variance is the same thing but without the square root, but the standard deviation is like this, right? So first let's compute p norm of, so let's set it to 78 and discuss what's going on later. So q equals 78, and then we'll say mean is 0.65 times 100, so that's 65, and then sd is, so we can just leave it as square root of 0.65 times, so 1 minus, it's 1.35, so that's just 1 minus 0.65 times 100, right? So now here there's a bit of a problem because, so we're trying to estimate p binom of this, right? So here it's like 78 or less, so that includes like all of 78 is the intuition. Here this is like 78.0 or less, so it does not include like 78.1, but intuitively it should. So kind of for different configurations it's going to be a little bit different. So in general, the first thing you would try is like 78.5. Here what works out well as an estimate is q equals 78.9. Like you don't need to know this for an exam, like except to know that, yeah, like, if you do q equals 78, you'd underestimate p binom q equals 78, because with p binom you're including like all of 78.
Right.
With p norm you're just including 78.0 but not 78.1. And now we do 1 minus and hope that we get something that's similar. And indeed we do. So one possibility is, instead of doing this, is to specify lower tail equals false. That would be kind of the same thing, right? So you can say just this without the 1 minus, but with lower tail equals false. And that would be true. And that would be the same thing.
Okay.
All right, so that was question 1. So for problem 2, we're saying like, so this was a little bit confusing to some people. So like you're giving those numbers. So I happen to tell you that you generated them like that, right? But what you're given is those numbers, and what you want is evidence against the hypothesis that the mean here is 0. Like if you know that you generated them like that, then you don't need to do anything because you know that the true mean is 0.1. So that's that. So you pretend that you don't know that, and you're saying, well, if I generated those numbers, what would be the probability of observing something that's as extreme or more extreme? So let's do that. So let's save that as x, right? And so let's look at those numbers. So the mean of x is 0.81, right? The SD of x, we can compute it, so that's apparently 2.4. So here what we're saying is all that we know is it comes from a normal distribution with mean u and variance sigma squared, right? So what we want to know is how far away from zero is it, kind of considering the fact that the standard deviation here is 2.4. So that's a situation for a t-test, right? So you can do it with t.test, but let's do it manually. So we'll compute the t statistic. So the t statistic here would be, so the mean of x, right? So the mean of x, right? Minus 0. So that's like under the null hypothesis, the mean would be 0, right? And then divided by SD of x divided by the length of x, right?
Not square root length of x.
Right, square root. Right. Okay. Okay, so that's the t. So we can look at what the t is. So here it happened to be positive. Now, to be sure, what we can do is we can just say absolute value of that and then do minus the absolute value so that we are sure it's like the negative version of the t, right? So if it were 1.07 before, it would be 1.07 now.
Why is that important?
Well, because it's like more convenient, because then we don't have to worry about whether it's positive or negative, right? So like if we know it's positive, like we'd have to do just like minus that. But this way we know it's negative. So now we can just do 2 times pt of t with df equal to length of x minus 1. And that would be the number. So 0.3. So that means that we don't have strong evidence against the mean being 0. So now it's like the same thing as in Precept 9, right? So now let's do it like this.
Sorry, quick question.
Yeah.
So we use the t statistic because we weren't given the standard deviation.
Correct. Okay. Yeah. Well, we know what it is, but we assume that we don't, because of course, like we could also assume that we know the mean, and then there's nothing to do, right? So now let's try it for like a really large number, and obviously, kind of what we expect is that if the number is really large, then even a small difference would really show up, right? So it's so large that we actually have to wait a bit to get it, but now there it is. And now we can do, again, 2 times pt, and it's just 0, right? So, okay. So that's that. So 0 means we definitely reject the hypothesis that the mean is 0.
And that's just because we have more tosses.
Yeah. So, okay. Well, not tosses, but like observations.
Yeah. So if you have more observations, that just means like it's more, like it's farther away from mean, or? Well,
no, I mean, it's going to be the same thing. Like if you do the mean of x, like it's not going to be, so the mean of x is going to be 0.1, right? It's going to, so I don't remember what the mean of x used to be before, but like, so it's apparently 1, so it was even further away actually, right? So actually this is like, obviously this is like a really good estimate for, so what changes is the length of x, right? So because if you have like this many, I don't even know how many, but like many millions of observations, and the average is not 0, then you know that like it's not a fluke, right? Because that average doesn't vary very much at all. In fact, we know how much it varies, right? So if you know the standard deviation, so the standard deviation is 2, you can compute the standard deviation of the sample mean. So the standard deviation of the sample mean would be sigma, so 2, divided by the square root of this. So, and this is like a measure of how much the sample mean is going to vary. So it's going to vary by this much, which is not very much at all. So you'd expect kind of some deviations from 0.1, but not more than 3 times this much. So, and 3 times this much is not, like it's not close to 0 if you go away from 0.1. So that's why the t-test is really sure that the mean is not 0. Okay. So, okay. So here, well, problem 3 is really, really similar, though, to what we did in Precept 9. So I think we'll refer people to Precept 9. Mm-hmm. Okay. Okay. So let's, yeah, okay. So the take-home challenge, we'll do a separate thing maybe, but that's not on the test.
Wonderful.
Okay. Okay. All right.